Here's our 4 compounds with their bone structure. And we need to determine which, between the first 2 and the last 2, which of these 2 is more acidic and which of these 2 is more acidic. So we can determine this by looking at the stability of the conjugate base. So if we deprotonate all these, let's draw the conjugate base. Well, there's one of the triple bond. And if we go ahead and just draw all of these, removing the hydrogens there, I suppose there's also a hydrogen on this carbon that is still left. It's implied that it's still there, but if you were just confused by how I drew that, there is still a hydrogen. So in the previous chapter, we talked about size of orbitals and that s orbitals are quite a bit smaller than p orbitals. And we also said that the greater contribution of s that you have, the smaller the orbital is. So when we're talking about hybridized orbitals, the more s character you have, the smaller the orbital is because s orbitals are smaller than p. And the more p orbitals you have, well, the larger the orbital is going to be because you're combining more p's with one s. So let's look at the hybridization of each of the carbons that are the carbanion. Well, our first carbon here is sp hybridized. That tells us it has 50% s character. If we look at the next compound, that anion is sp3 hybridized, meaning that orbital has 25% s character. So if we're just thinking about the orbital that these lone pairs are sitting in, this one's in an sp orbital, this one's in an sp3 orbital. Now, this isn't drawn to scale by any means, but I'm trying to show you that the sp orbital is going to be much smaller than the sp3 hybridized orbital. Therefore, this lone pair of electrons is held more tightly to this carbon than to this carbon. Therefore, this hydrogen is more acidic because this compound or this intermediate is more stable. The anion is more stable on the triple bond than just on a regular alkane due to hybridization. Let's look at the next 2 compounds. Well, the top carbon is sp2 hybridized, which is 33% s, so 1 s and 2 p's. So 1 divided by 3 is 33, or 0.33, which is 33%. And for the bottom carbon, we have sp3 hybridized again, which we said was 25% s. So again, sp2 hybridized orbital is going to be smaller than the sp3 hybridized orbital because it has greater s character, smaller orbital, held closer to that carbon, making the anion more stable than that of the sp3 hybridized anion. So which is the most acidic between these 2? Well, the one with the triple bond, the one with the more s character on the hydrogen you're removing, if we're just talking about carbon. The bottom one, well, it's the one that's sp2 versus sp3, again, because of greater s character. Finally, they want us to determine between the 2, which is a stronger base then. Well, we said this was a stronger acid, so that means the conjugate base is more stable than the other compound. So that means this compound is more reactive. Another way to put that, if you want to look at it this way, the lone pair is in a larger orbital. It's more available to, say, attack a hydrogen and act as a base than this orbital because it's held closer to that carbon. This lone pair can reach all the way out here. It can more likely come in contact with a hydrogen, and it's more willing to give up that lone pair of electrons to become stable. This anion is more reactive because it's less stable, is another way to look at it. So therefore, this anion is more basic. Same is true with the bottom case. The sp3 hybridized anion is more basic. That orbital is larger. This anion is less stable than this one.